In this video, we'll take a look at the Pythagorean Theorem, which is central to trigonometry. We'll be using it all the time. So the Pythagorean Theorem deals with only a right triangle, and the three sides satisfy this relationship: a squared plus b squared is equal to c squared. So I think of it as the sum of the squares of these things that we call the legs. The legs are the things that make the right angle, and then, of course, the hypotenuse is the longest side. The hypotenuse is opposite the right angle. Okay, a couple of cool applets that I want to show you that kind of show you how the Pythagorean theorem works. We'll even probably look at a real simple kind of proof of this. I kind of like this thing right here. This is it's a puzzle, what it is. And what you've got here is let me reset this thing right here. And you've got your triangle right here, represented by the sides A, B, and C. So this represents the area of A. So if you did A times A, you would get a square. And then this over here would be B times B, that's a square. And then this out here would represent C squared. So when you think of A squared, you're thinking of the area of this squared. B squared is the area of this squared. And c squared is the area of that square. So this is a cool thing. You can just kind of slide these things over, and we're going to see if I can do this. I'm putting myself on the spot here, so I hope I can pull this off okay. Let's see. So I'm going to move this over here, and I'll try to rotate this thing if I possibly can. Okay, something like that maybe. I did this beforehand, so there we go. I think it's going to be like that. We'll put that right there. Okay, and let's see. How about this thing? Let's slide this, kind of adjust this somehow. Not like that. Let's try it maybe like that and see if that'll work. Yeah, I think we got it now. Then we can put that triangle there. Okay, and then this triangle right here could be rotated, it looks like. And then it'll fit right up there. So that's kind of a cool little puzzle. That shows that those, you could divide that up and show that those two areas add up to that area C like that. So I think that's kind of a cool little thing to look at then. A couple other things. Let's see, with this one, I think I had a little rearrangement proof here that's worth showing. Here's a right triangle right here, and I can kind of slide these things a little bit here. And it turns out that it doesn't really matter what the sides are. They're always going to satisfy that relationship in there. So I don't really know what this thing's supposed to do. I was looking at this beforehand, and I thought it was going to show something pretty cool. I don't know what that's supposed to do. Okay, it looks like it's totally pointless. Okay, here's how it goes. So we got my triangle. So if I drag this slider, what it's going to do is it's going to take this triangle and it's going to reproduce the same triangle at another end. Then we'll keep kind of going through it again. It's going to make a next rectangle and then a next rectangle like this. So what you're doing is you're formulating this diagram right here. So we have the original triangles with side A, B, C. So we're trying to show that a squared plus b squared equals c squared on this. And this just kind of takes you through a way to visualize this. Now I'll move this like this. Okay, and then I'll move this like this. Okay, so now what we have is we have a squared plus b squared. And see, that whole thing right there now is going to be equal to c squared. So that's kind of a cool little thing to show on there, the way that works. Okay, there's several of these things on the internet that are pretty cool to show students. That's one of them. Okay, let me go back to see if there was another one that I wanted to show you. Just one more. And this one's kind of the classic one that that's a good thing on GeoGebra to show to students. And this kind of goes like this. So basically the idea is like if you have a triangle, and I can manipulate this so I can get the sides. I'm going to try to make this like go down to 3. because it's kind of nice if you can do that, then that's 5. And I'm going to make this become 4 just because this is kind of a special right triangle where A is equal to 3, B is equal to 4. It turns out that C is equal to 5 by the Pythagorean theorem. And if you do this, what this is attempting to show anyway, if you manipulate this, and this is like kind of inaccurate here. If you do 3 squared, that should be 9. If you do 4 squared, that should be 16. And if you do 5 squared, that should be 25. So what it's attempting to show you is no matter how these sides go, as long as you've got a right angle in there, then this side squared plus this side squared should always equal that side squared like that. So that's kind of the classic thing that I like to show students. Okay, so now in the bottom part of this, just a little bit of vocabulary here. We can always use the Pythagorean theorem. If we know any two sides of a right triangle, we can use the Pythagorean theorem to work out the length of the third side. Okay, so on the next page, one thing I wanted to mention, a little historical thing, that there was a U.S. president who proved the Pythagorean theorem, and he came up with his own unique proof. It certainly wasn't a modern president. This goes back to the 1800s. So James Garfield came up with a very unique proof of the Pythagorean theorem. So I'm going to give you one of the simpler proofs that I know. And we have this diagram like here. And what we're going to do is you see that we have the triangle ABC, which is a right triangle. And we're going to prove that a squared plus b squared equals c squared. So the way I look at this is we have this big square. And when we have this big square, we do the area of a square by doing base times height. The base would be equal to a plus b, and the height would also be equal to a plus b. So that would actually just be a representation of the area of the big square. Okay, but we can also put this together like this. Okay, we can put all of this 4 triangles together. So what we can do on this is the area of that big square should be equal to the area of these 4 rectangles or triangles. The way you find the area of a triangle is you do 1/2 base times height. So this triangle here, the base is A, the height is B. And there are 4 of those. So we have that. And then we're going to add on the area of this square, which is c times c, which is c squared. So what I'm trying to show you is if you look at the big square, it's just base times height. So it's a plus b times a plus b. If you look at the components of this, it's the 4 triangles plus the area of the square. Now let's just work out some simple algebra and you'll be amazed at how this works out. I could FOIL this out to get a squared plus ab plus ab plus b squared, like that, with the FOIL. I can go over to this side of the triangle. 4 divided by 2 is 2, so we get ab. And over here, we would get, and that would be 2ab. 4 divided by 2 is 2. And then this would be c squared like this. So what happens is you get a squared plus 2ab. Those are like terms. And then on this side, you just end up with 2ab plus c squared. So these things cancel out. You could subtract 2ab from both sides, and look at this. You end up with the Pythagorean theorem. So that's one of many proofs that have been discovered over the years of the Pythagorean theorem. So mainly what we'll do in this video is just kind of look at how you use a Pythagorean theorem to find a missing side. So A and B are always the legs. It doesn't really matter which is which, but C is always represented by the hypotenuse. So in this case, we would have, again, a squared plus b squared equals c squared is Pythagorean theorem. So we would have 4 squared plus 8 squared is equal to c squared. That will give us 16 plus 64 equals c squared. Then that would give us 80 is equal to c squared. Okay, now what you do in this case is you do a square root property. So what I'll do is take the square root of both sides. You're used to having a plus minus when you do a square root of both sides, but we're dealing with triangles, So the length of the side is always positive. So we would end up with c is equal to the square root of 80. And you could certainly take a calculator and do the square root of 80 and get a decimal approximation, but this is an irrational number. Those decimals go on forever without a pattern. So we don't usually do it that way. Usually what we do is just simplify the square root if we possibly can then. So we'll kind of avoid doing decimal approximations on these things then. Okay, so let me get this calculator set up so it doesn't disappear every time I click on it. There we go. Okay, so anyway, that would give about, if you rounded that off, that'd be about 8.94. But what we want to do is we want to break this up into two numbers that are, to see if one of them is a perfect square. Perfect squares are numbers like 2 to the second is 4, 3 to the second is 9, 4 to the second is 16. It turns out that 16 times 5 is 80, and then the square root of 16 is 4. So we end up getting, the best way to write the answer to this problem would be 4 times the square root of 5, like that. Okay? And it's always real easy on a graphing calculator to tell you're right on these problems. I'll just do this one time. But if I was to go 4 to the second plus 8 to the second, doing a squared plus b squared, you notice I get 80. Now if I do parentheses, 4 times the square root of 5, close parentheses and square that, then I'm going to get the same thing. So it's easy to take a good calculator and tell you're right in case you're ever in doubt. Okay, the next one, what we're going to do is we're going to find side A. So again, I'll just write down the Pythagorean theorem, a squared plus b squared equals c squared. We don't know what a is, so that will be my unknown. B is 15, so we'll do 15 squared. C is 17, so we'll do 17 squared. Okay, I can work out 15 squared is 225. You can work out 17 squared either by hand or on a calculator. That's going to give you 289. Then I can subtract 225 from both sides of the equation. And that will give a squared is equal to 289 minus 225, which will give 64. Then from here, I can do the square root property. So I get a squared equals 64. I can do the square root of both sides. This time, the square root of 64 is a whole number, so I end up getting a is equal to 8. So anytime that the three sides of your right triangle turn out to be whole numbers, we have a special name for that. We call this a Pythagorean triple. And there's an infinite number of whole numbers that satisfy the Pythagorean theorem. Okay, so that's what you'll kind of get into, is you'll do this all the time in a trig class. Okay, so what I want to do is one more here. And with this one, the hypotenuse is going to be C. I'll call that A and I'll call that B. A and B are interchangeable. So if I do A squared, I'll have 4 square root of 3 squared plus B squared equals C squared. And when I work this out, when you do this, there's a couple ways to do this. You can square the 4, and then you can square the 3. That would give 16 times 3, so that's going to give 48. You can also do this if you want to. You can just write it out twice. Squaring something means multiplying it by itself. So if you do this like this, it'd work out the same way. You just do, and it's not FOIL, it's just multiplication. So 4 times 4 is 16. Square root of 9, you'd end up having 16 times 3, so it's 48. So we end up with 48 plus b to the second equals 144. Now we can subtract 48 from both sides. And just take my calculator on that. 144 minus 48 is going to give 96. So I get b squared is equal to 96. Okay, so now I'm going to apply the square root property. And again, what I'm going to do is look for a factor, see if I can break this up. Now, you can use your calculator to help you a lot in the modern world with stuff like this. If you look at some of these perfect squares, you could try different things. You're always looking for the biggest one. So if you take 96 and divide it by 4, you get 24, but 24 is also divisible by 4. So if you go back to 96 and divide it by 16, then you get 6. So what we can do is we can break this up into 16 times 6. You can do it in 1 or 2 steps when you do that. So this is going to give an answer of b equals 4 times the square root of 6. Okay, so that's how you do. That's the number one thing that you want to be able to do with the Pythagorean theorem is find missing side of a triangle. So I'm going to have you go ahead and pause the video and work out these 3 problems. And when you're done, just check to verify whether you got these right. Okay, so you can check your answers and see if you got these right. The first one, the missing side was square root of 194. And by the way, the square root of 194 does not reduce further. If you can do what's called a factor tree. If you divide that by 2, you get 97. And then 97, there's nothing else you can do with that. You can't break that any further into a perfect square. There are times when the numbers get kind of big that you have to kind of play around with factor trees a little bit. Number 2, the answer should have been the square root of 2. Again, I'm doing 3 squared plus b squared equals square root of 11 squared. Going through the details of that, you would end up taking the square root of both sides to get 2. And number 3, you again have what we call a Pythagorean triple. And because you ended up with 3 whole numbers on this. So when I put this together, I went ahead and put the units in just so you could see how the units work out. So Pythagorean theorem, you have a squared, 7 squared would be 49 square centimeters, plus b squared, 25 centimeters squared is 625 centimeters squared. And then from there, you end up with b squared equals 576 centimeters squared. When you take a square root of something squared, it's itself. So I went ahead and just put the units in there so you can see how the units work out. If your problem has units, it's real important that you contain units in your answer. 1 and 2 did not have units, so you don't worry about it. But number 3, you do want to write those units on there. Okay, going to the next page, just kind of wrap this up. I want to talk about a Pythagorean triple a little bit. And Pythagorean triples, some of them pop up a lot. So to me, the 3, 4, 5 and the 5, 12, 13, those are the 2 that you probably should memorize because they show up a lot. The more you memorize, the better. But at a minimum, those are the ones you want to do. And again, 3, 4, 5 is a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. That one's a real easy one to see. And there is an infinite number of Pythagorean triples. So if you look at this, we get kind of a family of Pythagorean triples. So the primitive would be as reduced as you can. So 3, 4, 5 we call a primitive Pythagorean triple. If I double all the sides, I get another Pythagorean triple. If I triple all the sides, I get another one in that family and so forth. So every primitive Pythagorean triple, you can double, triple, quadruple, quintuple each side to get a brand new. Okay, so a couple of things I wanted to show you on a couple of applets here, and then that'll wrap up this second part of the video here. So this is something that's on GeoGebra. So let me open this up real quick and take us to the GeoGebra website. There's all kinds of great applets that people have put together over the years to show these concepts. This is a Pythagorean triple. This is a really nice way to show. You have a length that's 3. So notice you have this 3 by 3, or that would end up being 9. 3 squared is the area 9 of that square. 4 squared is 16, so that's the area of that square, and so forth. So this is what we would call a primitive Pythagorean triple. Excuse me just a minute here. I'll hang up on this salesperson. Okay, so if I double that 3 up to a 6, and then if I double this 4 up to an 8, then I get another triple on this. So I'm getting another Pythagorean triple, so just by doubling the sides. And it still satisfies that same relationship. Okay, so that's kind of a cool thing to look at. Another thing that's kind of cool is people have done scatter plots with Pythagorean triples, and they come up with real interesting things. This is a Wolfram applet that I found that shows how Pythagorean triples look when you plot points on a coordinate system. So it's kind of a cool thing to show here. So to begin with, this is going to show a two-dimensional Pythagorean triple. Let's see if this thing takes it a minute to kind of load up there. Okay. So right here, if we do our x-axis to 120 and y-axis to 120, this is showing some Pythagorean triples. Like, for instance, we have 3, 4, 5. All they're doing is plotting the A and B from the Pythagorean theorem. So 3, 4, another one on here, I think this one's probably 5, 12 from the 5, 12, 13 triangle, and like that. And basically, these Pythagorean triples go on forever. You can extend your x and y axis infinitely, and then they start becoming further spread out over time. You can superimpose them on top of each other, and when you do this, you get some kind of interesting looking patterns on Pythagorean triples. It's pretty fascinating to look at these things. The one that I had put in your notes is something kind of like this. And if you put all this together, these straight lines those are families of Pythagorean triples. So I think this line right here is the family created by the 3, 4, 5 right triangle. This one right here is probably the 5, 12, 13. So you get some kind of interesting patterns. I always think things like that are just incredibly cool. I don't know about you. All right, well, that should be all I want to show on this part of the video. So main thing you all need to know is how to find a missing side of a right triangle using the Pythagorean theorem. All right, good luck.